So welcome everyone to today's seminar, Hydrogen Production Technologies. So this is our second seminar, part of our hydrogen seminar series. Our first one was, we hosted it 2 weeks ago, Future of Hydrogen in the Middle East. In the first seminar, I'm happy to report that we had over 510 people attended the first seminar. And for this second seminar, we have 570 registered for this one. And actually, this shows that the appetite and the interest is very strong for the hydrogen topics. So today, our seminar is on hydrogen production technologies. And in this seminar, we will be reviewing the various research development needs and current hydrogen production technologies from both hydrocarbon resources and water. And we will be also reviewing the different pathways for ammonia production as a hydrogen carrier. So I will now give the floor to Professor Andy, our moderator for today's seminar. Professor Andy is currently Professor of Chemistry, and he is the Associate Vice President for Research at KAUST. Professor Andy.
Thank you, Mohammed. Good afternoon and good morning, everyone. It's really my privilege to have this opportunity to come here to serve as the moderator for today's discussion, a topic I'm also very interested. And today we have three excellent speakers. Without further ado, let me introduce our first speaker, Dr. Joe Powell. He received his bachelor degree from University of Virginia in 1978 and a PhD from University of Wisconsin-Madison in 1984, both in chemical engineering. He is a fellow and a former director of the American Institute of Chemical Engineering, and it has served as Shell's first chief scientist in chemical engineering from 2006 until his retirement in the end of 2020. He has chaired the U.S. Department of Energy Hydrogen and Fuel Cell Technology Advisory Committee and was elected to the U.S. National Academy of Engineering in 2021 after serving 2 terms on its board on chemical science and technology. So today, he will be sharing with us a topic related to blue hydrogen via reforming and gasification. Dr. Powell, the stage is yours.
All righty. Well, thank you for that kind introduction, Professor Andy. And let me share my screen here today. Are you seeing that okay? Well, good.
All is well.
Super. Well, it's an honor to be here today, and very exciting topic of hydrogen, which is dominating the news. So as Professor Andy indicated, I'm retired Shelf Chief Scientist of Chemical Engineering and just starting up now the University of Houston Energy Transition Institute. I'll be talking about hydrogen via reforming and gasification, and especially the blue hydrogen angle. Let's start with some context. So hydrogen market growth is really as an energy vector. So you can consider it to be the diesel or liquefied natural gas of the future. And the key point is the ability to move energy from resource-rich regions to those that are don't have quite that resource availability, whether that be natural gas or renewable energy. If you look on the bottom left from the Hydrogen Council, you see the dark blue areas where you have abundance of natural gas, the light green where you have quite a bit wind and solar renewable energy, and then the turquoise, such as the Middle East and the US, Australia perhaps, where you have both. And so the decision for industry is whether to invest in the blue or the green, and how are you going to move energy into markets. The key point is the energy density of hydrogen and its carriers is much better than trying to move energy, especially the renewable electrical energy via batteries. So the vector is the key point. and the expanded market growth. If you look on the left-hand side, you see the Hydrogen Council and McKinsey's estimates of what the price of the current gray hydrogen today from natural gas reforming versus the blue, which would be natural gas reforming with carbon capture and storage, or CCS, and the green, which is the electrolytic hydrogen, which Chris will talk about here shortly. Today, the blue option is considered the lower cost way to go, but the electrolysis route is catching up rapidly. And so we'll talk a little bit about that. You see the cost curve going up here from the Hydrogen Council, and that's because of the assumed carbon tax that would be coming in on the CO2 emissions. So if you look at this 2021 report, on the right-hand side, they are estimating on the projects announced, what is the capacity going forward from the projects today in terms of green and blue as we make this transition into 2030. But the benchmark price there on the left-hand side is $1 a kilogram hydrogen, and electrolysis may be perhaps 3 times that today, but coming down rapidly. Here's some further breakdowns in the numbers. Again, gray on the left, blue in the middle, and green on the right. And you see that carbon tax coming into play by 2050-ish, according to this analysis. The gray is certainly mature. Blue, natural gas reforming is mature technology with the CCS. And the green is still developing on an S-curve and coming down in cost. And so that is the dilemma from the investment side. On the right-hand side, you see that growth in demand. So again, hydrogen is going after new markets. It's going after transport markets, industrial heating, residential, and et cetera. And that explains the tremendous growth anticipated in future demand. If you look at where the hydrogen economy is emerging, and I'd point out that I'm going to leave copies of these slides with everyone so you can sit back and relax and don't worry about taking notes, because you'll have all these slides at your disposal after the event. But you see a lot of activity in Europe because they're somewhat energy poor and need and are looking for that clean energy. And Japan being another market for that clean energy. And then the rest of the world is either using or trying to supply that. So you see activity in Australia, New Zealand, South America, US and Canada. This particular publication says 228 announced projects for the year 2021. That may have been more like 370. And so there's just quite a bit of project and investment project scouting going on in the hydrogen space. Now, I'm going to be talking today about the natural gas reforming, biomass and coal gasification, some of these large centralized ways of producing hydrogen today. You can, of course, also make it in a distributed manner, and electrolysis in particular plays out well there. And of course, there are other ways to make hydrogen as well, but we will focus on the natural gas reforming and some of the other gasification routes. Important to keep in mind is it takes less energy to reform or split hydrogen off of methane. In terms of the kilojoules per mole, it takes a lot more energy to split water in terms of water electrolysis. However, if you're reforming natural gas by steam methane reforming or methane pyrolysis, which we'll talk about shortly, it takes less energy, but you have to be able to sequester or use the carbon into products. We'll also talk about partial oxidation, where you're actually partially combusting the natural gas in addition to making the hydrogen and using that to export energy and provide your process and utilities heat. Some key references to have if you're working in this space: you want to grab the IEA greenhouse gas report from 2017, which is sort of the standard for the techno-economic analysis on steam methane reforming. Very good reference there, process from Foster Wheeler. And then also a good one from the United States is this techno and economic potential of hydrogen at scale within the US, and it covers the economics of the various plausible routes to hydrogen, and very good sources of technology and economics for those routes. When you look at hydrogen reforming from natural gas, it's essentially a large furnace. So you have a furnace with many tubes running down. And so you're really applying natural gas, not only to the process side, but also to the furnace side of that unit. If you move to something called autothermal reforming, you're actually blending oxygen in with the process side and producing the heat in addition to the process chemistry in an integrated manner. And then again, if you go to partial oxidation, or what Shell would call gasification, you're adding excess oxygen so that you can not only generate hydrogen, but also produce steam and electricity. So the red circle here shows a person on top of a steam methane reformer furnace. So these are huge units. You see some of the temperature profile here and a little bit of what that equipment design looks like. In terms of the tubes, this particular example had 900 tubes. They're about 10 centimeters in diameter. And when you're running this reforming reaction, you do leave a little bit of carbon monoxide in the off gas. And so you have to run the water gas shift reaction to fully produce all of the hydrogen that's available from the natural gas feedstock. It's an equilibrium limited reaction, so it needs to run at above 750 degrees C to drive to high concentrations of hydrogen, or you have to have a novel integrated separation technique to drive that equilibrium if you want to do a sorption enhanced play or the like. Catalysts, so a nickel catalysts are used for steam methane reforming, and then different iron oxide, chromium, or copper catalysts used for the various stages of water gas shift in order to complete the conversion of the carbon monoxide intermediate over to the hydrogen. World's largest plants, a couple of them in the Middle East and the UAE, and then also in Kuwait. Here's another one listed in Brazil, Russia, and Turkey, but these are very large scale plants. Work is still being done on SMR. So as you look at decreasing carbon footprints and making them more efficient, you see quite a bit of patent and development activity going on in terms of heat integration, pinch analysis, in order to make a more efficient integrated process. Here's a Praxair publication on a minimum steam process in terms of how the SMR unit could be integrated and designed. Now, one of the best papers, a lot of the cost information and detail is proprietary by the vendors, but a very good paper from Parkinson at Imperial College, which gives their own estimates of what the various hydrogen cost technologies are, but also compares the literature estimates from the SMR, the gray hydrogen, the SMR with CCS, which would be the blue, coal gasification, the methane pyrolysis, but also the biomass that I'll talk about today, and then the electrolysis. Now, these were the numbers before inflation hit from about 2 years ago. And so now you really have to consider the local natural gas prices in more detail, and then the dropping prices in wind and solar in order to make these comparisons. But overall, SMR with CCS is at the lower end of the cost production. Here's an optimistic projection for methane pyrolysis. Biomass runs a bit higher and is smaller scale in general. And again, the electrolysis is coming down in price because of developments in electrolyzers and improvements in solar and wind power costs. Nuclear can be lower costs, but usually you need to be running sulfur iodide or cycle, some of the more complex nuclear technologies, and not the steam reformers. These costs are highly dependent on how much decarbonization you're getting. And so when you're looking at a blue hydrogen, and especially, you have to say, well, how much CO2 reduction is coming into play there? If you look overall, steam methane reforming produces about 10 kilograms of CO2 per kilogram of hydrogen. And so you're looking at carbon capture and storage in order to reduce that and drive that into what is considered a clean hydrogen regime. You can also consider, where are you going to capture CO2? If you're in an SMR process, steam methane reforming, I mentioned you have a furnace side providing the process heat, and that generates one set of CO2. And then you have the process side, which is generating CO2 in the process itself. And so you end up having to capture CO2 from a couple of different points. And the process one is the easiest to capture. And a number of people are doing that to get to partially decarbonize, but getting to a high level of decarbonization of 90% is a bit of a challenge. Here's some numbers of what the Shell process SMR in Scotford, Canada is looking at. So they're taking it after the high temperature shift reactor before the PSA is where it was chosen quite a bit because of the advantaged pressure situation and CO2 concentration. And here's a picture of that particular plant and up and running, and in this case, injecting the CO2 in a deep saline aquifer and proving that that can be done. And this was primarily used to decarbonize some of the heavy oil refining operations to make it compatible with the base case assumption of petroleum in the California markets. Comparing the different approaches, blue hydrogen, again, you can do SMR. You will have to capture CO2 from a couple of different places if you want to do a high level of decarbonization. Autothermal reforming, you add just enough oxygen in the feed so that it becomes energy neutral and you don't have to be running that external fired furnace. And then if you go further and do, this would be shell gasification or partial oxidation, you're actually adding an excess of oxygen so that not only are you producing all the heat you need for the endothermic reforming reaction in the process itself, but you're also exporting steam to run all the process utilities. And so Shell practices gasification at some of its large units, the Pearl gas to liquids unit in Qatar, also in the Pernis refinery. So it's known technology. And looking at it from a greenfield investment point of view, there are advantages in doing the partial oxidation. It's non-catalytic, direct heating. And again, you can generate all of the power you need to run the process and combine that into your CCS unit. So when Shell looks at the numbers, they see a bit lower CapEx for the partial oxidation approach to future hydrogen. The key point is that if you're going to be removing CO2 from your hydrogen production, then the ATR and the partial oxidation are advanced technologies relative to the steam methane reforming. Unless you do something else there. One of the things you can do with steam methane reforming is actually add a partial oxidation step in series with your reformer, which is talked about here in this paper from iChemE. So that might be involved in a retrofit opportunity. Another key point is how much CO2 footprint is left in that hydrogen. So this chart from American Clean Hydrogen is saying that the blue hydrogen, the SMR reforming, can achieve the target of 2 kilograms CO2 per kilograms of hydrogen. And that is for the process itself. Electrolysis can be bad on the right-hand side if you have not decarbonized the grid. And of course, you have all the renewables options here on the left, which can easily meet that particular target. Have to keep in mind that the indirect global warming potential of hydrogen has been increasing via the scientific studies of the last a decade or so. And so it's now not considered to be totally inert or zero, has a global warming potential of 11. And the hydrogen leakage rates are becoming a concern. So if you replace the entire fossil economy with a 1% leakage rate in hydrogen as a carrier, then that would back off about 2% of the value of that decarbonization. And if the leakage rate is higher than that with these newer global warming potentials, then that can be up to 10%. And this means that there's a move to consider more distributed production of hydrogen and really worry about some of those distribution methods and pipelines in terms of what that leakage can be. So some of the stakeholders are giving a little bit of pushback in terms of how are you doing that hydrogen supply chain coming off of those large central units. So that needs to be taken into consideration. Another one is the methane leakage. So beyond the process itself, you have to consider the greenhouse gas impacts of the methane emissions, which can be on the order of a global warming potential of 25 times CO2 on a 100-year time frame, or up to 100 on a 20-year time frame. And so a lot of the stakeholders are pushing back in terms of what does that supply chain look like. And that can be especially difficult if you're producing by unconventionals and fracking and your gas operations. So that is something that the industry needs to get a hold of. We have a paper here from the EU and the US. Yes.
Dr. Powell, due to the time limitation, could you conclude your presentation within another 4 to 5 minutes?
I'll be doing that. Yeah. So the methane emissions need to be actively considered, and it is a challenge for the blue hydrogen, such that you really need the high percent capture as coming off the POX on the order of in excess of 90% in order to really achieve the clean hydrogen targets. And to do that, organizations are forming for responsibly sourced gas to really certify the methane emissions along the supply chain to the natural gas reforming plant. Now, as mentioned, you can also gasify coal. That's done quite a bit in China, and use that for the hydrogen production. Biomass is similar to that and presents some somewhat new challenges. There are multiple routes in terms of ways to be gasifying the biomass. And looking at that, you're introducing oxygenates into that equation. And it's surprisingly difficult because of the tar formation and biomass gasification. And to get to reasonable scale, when we were looking at biofuels, you needed about one of those trucks a minute in order to be unloading from the resource in order to develop a world scale plant. So complex technologies in terms of multi-phase reactors involved in the biomass gasification. You can also consider landfill waste and the bio components of that in terms of where that hydrogen can be coming from into the future. Capacity factors for the biogasification are higher than renewable energy from wind and solar in most parts of the world, and that's one of the attractive features of considering that as a feedstock. Methane pyrolysis being the other approach. So instead of making CO2, you can split the methane into carbon, solid carbon, and hydrogen. Those solid carbon products could be carbon fibers to make 3D printed automobiles or advanced housing. C0 is one company that's doing that using high temperature molten salt type configurations. Karlsruhe KIT has been investing the liquid metal approach, as has been MIT, which is a real materials challenge. You can get to very high temperatures there and drive the conversion reactions very well, but the materials challenges are significant. And the DOE has been sponsoring work in that space, both to make large volumes of hydrogen with carbon black as the product, but then small conversion also to make structured carbons for building materials or in that R&D space. And so you see a number of companies and entities that are pursuing methane pyrolysis. It's a great technology for places where you don't have the ability to sequester carbon. And Monolith, a plasma company, received $1 billion loan guarantee from the US government to develop methane pyrolysis and carbon black co-product in the US. So that's my talk today. Hydrogen via hydrocarbon reforming. You can get to the high capacity factors, 24/7 operations. It has the lowest production costs today. Methane pyrolysis can be considered where you can't do CO2 storage. And certainly it's under challenge because of the reducing costs of future green hydrogen by electrolysis, which you'll be hearing from next. So thank you for listening, and I'll turn it over to you, Chris.
Thank you very much. And we will keep all the Q&A section in the end of all the three presentations. The second speaker of today is Mr. Chris Copiano, who is the member of the engineering management from the Neo Hydrogen and is the director of contract research and development. And he was recently asked to lead the conceptual design and installation of Neo's largest PIN electrolyzer system today, a 20 megawatt plant that is providing green hydrogen to an ammonia synthesis process in Puerto, Spain. So Chris, the floor is yours.
Great, thank you for that introduction. Let me just get my screen here. So hopefully everyone can see that. So yeah, so Chris Capuano, I'm the Director of Research and Development at Neo Hydrogen. I've been with the company for just about 25 years, and so I've had a fantastic opportunity to take part in a startup company and then be part of this larger vision of green hydrogen to support many industrial processes as well as energy capture of some of these large renewable installations that are being cited. So my talk today, is going to be more of an overview of our company, really what we're focused on and the direction that we're going, to give you a sense as to the maybe the acceleration of the technology to try to meet the these emerging markets, as well as driving down the cost to get better penetration into some of these renewable capture areas. So quickly, just the company, we've gone through a lot of iterations, as you do over 25 years, where we've been sold, we've been bought, we've acquired other companies. Our most recent development was back in 2017, where we were acquired by Nel Hydrogen, a company in Norway that specializes in alkaline electrolysis. They purchased us really as an asset to expand their portfolio. My location in the United States focuses primarily on proton exchange membrane electrolysis, at a little bit of a smaller scale than alkaline can deliver right now, but we're trying to close that gap significantly. One of the other purchases that our company made was for a compression, storage, and dispensing company, so we could really have the full portfolio of options available for the customer. So not only do we have multiple technologies for hydrogen generation through either alkaline or proton exchange membrane electrolysis, water splitting, but we also have a fueling company located in Denmark that builds the actual infrastructure to be able to supply fuel for light-duty vehicles and heavy-duty vehicles. So the two technologies, as I mentioned, one of them is liquid alkaline base. It's a very old technology. It's well known. It's well understood. There's still some opportunity to reduce cost there. The reason that it's so intriguing right now is because of its ability to meet scale. We routinely will get 100, 200 megawatt orders for this technology. The drawback is that it has to use a pretty caustic electrolyte still. The scale and the footprint is very, very large. Where the proton exchange membrane technology comes in is that it can run at much higher current densities, meaning that you can get a smaller form factor for these sites, but also run it at a much, much higher current density, which allows you to significantly reduce your capital expense for the same rate of hydrogen production. The drawback, it still uses pretty expensive materials. Because of the low pH acidic environment, we're limited by the materials of construction. Typically, a lot of the metal separators that we use are formed out of titanium. The catalysts, as we know them today, are platinum and iridium primarily, although there's significant research being done by our Department of Energy, ARPA-E, and other agencies to try to understand how we can maintain the same activity of the platinum and iridium materials, but look to swap it out with maybe materials that are a little bit more readily available and cheaper. The work is still ongoing. There's a lot of work there to close that gap. So just two real quick images of these large scale installations that we talked about. So I mentioned that the alkaline technology is pretty old. You can see the picture on the left shows an installation that was done back in the 1950s, 135 megawatts tied directly into a dam. It's powered by hydropower. And so what we've been able to do is really leverage that base understanding of manufacture and scale and be able to apply that to some of the growth that we're trying to experience on the proton exchange side of things. And really what that is manifested in is this installation that we have on the image on the right. And so this is the plant that I was lucky enough to have led the concept development and deployment of over the past couple of years as I was pulled out of the research group to lead this. So this is a 20 megawatt installation. It makes about 4 tons of hydrogen a day, I believe, when it's fully running. It's tied into a 100 megawatt photovoltaic array and is producing 100% green hydrogen to an ammonia synthesis process on site. 20 megawatts sounds large. They're still viewing this as a demonstration of the technology. We really think that we need to get this into the hundreds of megawatts to be able to provide a 100% solution to some of these different industrial processes that require hydrogen. And we're trying to do that entirely green. I will say, as of right now, the plant's been fully commissioned. The keys have been handed over to the customer, and everything seems to be going okay. So our base business here is really pretty broad. So we've been fortunate enough over the past 25 years, 26 years, to be able to produce equipment that provides hydrogen for industrial applications while we waited for these emerging markets and energy capture to really start to take shape. And so what that's allowed us to do is focus on the durability of our systems and really improve the life of the overall devices. Now our systems and our competitor systems are all expected to run about 80,000 hours over the entire life. And so the durability is really, really key. Now that we've been able to demonstrate 8 to 10 years of continuous life running 24 hours a day, 7 days a week, we're really starting to look at the efficiency right now, because the efficiency is really one of the areas that we historically have not been challenged on when we've been selling hydrogen or selling these systems as an industrial gas provider. But it's very, very critical when we tie into these renewable sources to improve the efficiency, and that ultimately helps to really drive down the cost, because the total cost of ownership of one of these systems is more heavily weighted on the operating expense and the electrical expense over the life of the system. It's probably as high as 60% of the total cost, with the capital purchase being the other 40% or so. So the systems themselves provide, a very high purity hydrogen for whatever the application. We can produce hydrogen about 5 nines pure. And as I mentioned, while we've been selling this typically as an industrial gas into any market that requires a reducing environment, say silicone wafer manufacture, heat treatment ovens, that's been fantastic. It's allowed us to sustain ourselves as a company. But really where we want to be is really moving towards hydrogen as a means of capturing energy and using it for either fuel cell vehicle fill-in or power to gas, where essentially we'll take stranded renewable or renewable input, store that hydrogen to either be run back to a fuel cell, or as the previous speaker discussed, to combine that with ammonia and use that as a more efficient energy carrier. So our facilities are located in 3 different areas across the world. The place that I will be going to shortly after this talk is about 10 minutes from where I live in Wallingford, Connecticut. We do all of our proton exchange membrane research there, as well as manufacture of our industrial products. We've delivered over 3,000 units to date. It's probably closer to 3,500 units, with an internal capacity to scale up to about 150 megawatts of capacity annually without any changes to the infrastructure right now. We currently only run 1 shift, 8 hours a day, and we're able to do 50 megawatts a year. Our facility over in Norway, this is our first automated facility that just got commissioned earlier this year. It has the ability to do 500 megawatts of alkaline electrolysis a year, and the building itself can be scaled up to 2 gigawatts a year. We just recently got approval from the board of directors to add another 500 megawatts. So the facility in a few months' time will have the ability to do 1 gigawatt of electrolysis a year. And then our facility over in Denmark that exclusively does fueling, where we can do 300 hydrogen fueling stations a year, and that includes compression, storage, and dispensing. So as I mentioned, the plant that we have over in Norway recently went through a commission and a christening activity of a new facility that we built that we're really going to use as the model for expansion in all of our different facilities as we move more and more towards large scale automation. So you can see the bottom image at the left. It's a large plant. Everything's computer controlled. We have fantastic insight as to where a material is, all the way from where it's received in as a raw material, all the way through to when it's being packaged into a commercial system that is going to go to our customer. I'll just show one more picture here, and it's really exactly what you'd expect. It's an automated line with robot arms and pick and place items to be able to do this in a completely autonomous way. It has real-time kind of control and monitoring, which allows us to track a part all the way through, understand the status, the quality of all of this. So I say this because I as the research and development director, I do primarily focus on fundamental research and early stage development and enhancement of our existing lines. But because we have to do split jobs between both R&D and also support the manufacturing groups, when we're doing the fundamental research, we always have a vision as to what it needs to look like when it moves to our manufacturing group. It has to have that manufacturability in mind, not just manufacturability, but manufacturability in high volume throughput and at scale. And so that's always in the back of our head when we're doing our fundamental research of really where does this ultimately have to go? And am I designing and developing something that's going to be easy to translate to some of our manufacturing space? So now as I focus and pull away from the alkaline area of the business and start to focus a little bit more on what I do on the proton exchange membrane side, I'll just talk a little bit about our location. This building we had constructed back in 2001, specifically for us. So it's built with research and manufacture in mind. You can see really the chart on the right is meant to show the ramp up of our deployment of megawatt scale technology over the past few years. You can see, early 2000s, our deployment, because our systems were much smaller for this industrial applications, the amount of deployment of megawatt capacity was pretty low. But in the past couple of years, as our systems have gotten larger and as our orders have gotten larger for some large installations, our deployment of megawatt scale systems has significantly ramped up, and we expect that to grow significantly over the next
Hello?
Yes.
Hello? We lost you for a few seconds. Could you repeat?
Oh, sure. Sorry about that. We have a thunderstorm right now, so it's possible that.
Okay, now it's better. Yep.
Okay. Yeah, so I was just saying really quickly on here, the bottom right graph that we have is really just supposed to show how our product line has grown, and we've been able to accelerate the deployment of megawatt systems out into the community as the technology has become more widely accepted and the markets have become larger. So the future of Nell's PEM manufacture. So we're going to follow the model of our alkaline parent company over in Norway. So right now we're actively looking at a new site within the United States to be able to deploy our PEM automation facility, with the intent of having something, so a location selected by the end of this year. And then next year we'll begin the build out, and shortly thereafter, by end of 2023, we'll have 500 megawatts of manufacturing capacity within the United States for our PEM site. Shortly after that, we're going to roll out additional lines to increase the capacity, with the goal of being able to reach 2 gigawatts of automated capacity in the US within the next couple of years. And so what we're doing right now to be able to realize that opportunity is we're evaluating all of our manufacturing processes. And so we have older methods, they're sheet fed processes, which really can't keep up with the scale and the volume that we need for our systems. So we're looking at new processes in order to migrate our existing manufacturing techniques into new, higher throughput, computer controlled techniques. And so the image that we have here really just shows in the top right image our current process of making electrodes, where it's essentially a silk screen process where we're just depositing electrodes onto a substrate. The bottom right image is where we're moving, where we essentially have roll-to-roll manufacture of electrodes onto membrane or substrates. And really what you would think of when you see a newspaper manufacturing facility, where it's a roll-to-roll manufacturer, you have really, really high throughput of your substrate going through as you're applying a catalyst ink on the surface of it. Fortunately, fuel cells have really led the way as far as this goes. We can take a lot of lessons from that. The technologies are starting to really converge, where fuel cells are very well known. They're very simplistic designs at this point, where they've been able to minimize the amounts of components and the different interfaces. Our technology is moving there as well. So we should be able to leverage a lot of the different automation that's been developed for fuel cell capacity already. Now, there's certainly some differences, but there is a lot that carries over. And so what does this allow us to do? So it not only increases our ability to produce higher volume parts at larger scale for components that really can't be handled by an individual operator right now. It has to be handled by large pieces of automated equipment. It allows us to really refine our manufacturing techniques as well. And so now that we move things that are a little bit more automated, computer controlled, the electrode depositions that we can create can become better controlled. We can make thinner layers on those, stretching our inventory and allowing us to do more with less. And what that ultimately translates into is improved interfaces, reduction of materials used, more consistency, more uniformity. And you can see in the top right image, really what we're looking at is if we have a baseline cost here, as we implement some of these automated processes and these roll-to-roll processes, we can significantly reduce the amounts of materials that we use in there, as well as the touch time and the labor content, significantly reducing the cost. And so what we're working towards currently is this roll-to-roll process in the third bar chart, which we hope to realize by later this year. And then this lower pressure MEA design sometime later this next year. Really, that's when I say lower pressure, it's the delivery pressure of the hydrogen. All of our systems are designed to deliver hydrogen at 30 bar right now, and we're looking at lower pressure applications at this point. So as I mentioned, I talked a lot about automation and large scale, but I do focus a lot on R&D and really fundamental research here that will eventually feed into these systems. And how are we doing that? So we collaborate with universities quite a bit to help us with a lot of the basic science work, as well as the national laboratories within the United States. And we can serve as the industry partner on there to help guide the research and provide a little bit of perspective as to what technologies we think will work, and which ones might be difficult to translate to manufacture. So we can catch a lot of that early in the process and refine that to try to tune some of these early stage developments into something that's going to be available for industry. And so you can see we look at computer modeling, we look at heat transfer, we look at thermodynamics, we look at flow distribution of gas and water in the cell. We look at material characterization for hydrogen embrittlement of these components to see how hydrogen might attack some of these different metal components. And then we come up with designs that are subscale, so these 90 square centimeter architectures, which allow us to evaluate these technical changes at a much smaller level so we don't have to incur large costs. But it's essentially a subscale model of our megawatt technology. And so we get very, very good translation when we do development on the small scale, knowing that it's going to be able to move to our 1,600 square centimeter active area devices pretty well. And as you move to that scale, the cost reductions that you have available to you is significant. So what are we looking at over the next few years? So if we look at our baseline cost of the electrolyzer system today, on the left, 100% of the cost, we're looking to reduce the overall cost by about 40% through some of these automation and research activities that we have going on right now. So we're looking at advanced designs of our cell stacks and systems. This includes exotic materials, looking at ways to use maybe cheaper materials construction, but then coat them with a material that provides a barrier to these cheaper materials of construction, implement process development and enable automation and continuous processing. On the engineering side, our team is looking to see how we can take that 20 megawatt system that we deployed earlier this year, and how do we move that to a 100 megawatt system and make it cost effective. We're looking at standardized design, a lot of prefabrication and skids that just get shipped to the location and get integrated at the point of delivery. And then our supply chain group is obviously working on procurement. And so as we get into these larger volumes and larger form factors, it gives us leverage with our supply chain to start to work on cost agreements to try to get some reduction in the overall cost of that. And we see that is all translated to about a 40% reduction over where we are today. And we have an internal goal, and we're ahead of it right now, and we're well on track to meet cost parity with steam methane reformed hydrogen by 2025 with some of these scale-up facilities. So we're very, very close right now. In a couple of years, we're going to be competitive with that. And I think I just have maybe one slide or left here. And so, some of these large installations and some of the scale of our equipment has allowed us to penetrate some of these really interesting projects that we have around the world.
Chris,
so, yep.
Chris, could you conclude your presentation in 2 minutes?
Yeah, I just have one slide.
Oh, thank you. Yes.
So as I mentioned, it really gives us a pretty large opportunity here to serve into a lot of different areas of industry. We have the ammonia plant at the top right, which we discussed already, hydrogen for green steel. And these are all actual projects that we've been awarded that are anywhere from 20 megawatts to 200 megawatts of installed electrolysis, offshore wind on an oil rig, as well as bus fueling that we have out in California. So this is the last slide that I have, and really it's just a summary of everything that we discussed. And so, we're the oldest electrolyzer company in the world. We have the most systems deployed in the world and have the most experience out of any electrolyzer company. We have equipment on every continent. So we have a lot of great experience that's allowed us to feed back into our product to further improve the reliability. And so we have really well-defined roadmaps. We see the market starting to take shape, and we're really excited to be part of that. And we're trying to position ourselves to get more of that opportunity and really be provide a solution to carbon decarbonization. So I appreciate everyone's time. That's the last slide that I have.
Thank you, Chris. Now the floor is open for questions. Do we have a question from the audience? Could you give a brief introduction of yourself and before you ask the question?
Hi, this is Soumitra. I'm a research scientist at Clean Combustion Research Center. I have a comment and a question for Dr. Powell. You mentioned about methane pyrolysis, but methane is not found in nature. It's the natural gas that is found in nature. And especially in countries like Saudi Arabia, methane content is roughly about 68 to 70%. The rest is carbon dioxide and hydrogen sulfide and many other gases with smaller quantity. Now, what I foresee is you will still need carbon capture because about 10% carbon dioxide is there in a country like Saudi Arabia. And then you have to scrub the H2S off. So this process will not be carbon alone that one needs to take care, but it will be carbon capture plus scrubbing of H2S and so on and so forth. That's number one. I want to know your comment about natural gas pyrolysis as opposed to methane pyrolysis. The other question I have is about life cycle emissions of air pollutants from manufacturing and processing of SMRs, ATRs, so on and so forth, because they do release SOx, NOx, particulate matter, which ultimately form ozone precursors and aerosols. And these ozone precursors and aerosols, they add to global warming or reduce global warming. So I do not see in the discourse on hydrogen this impact of air pollution which certainly needs to be there in my humble opinion. Thank you very much.
Well, two very good points about moving from the laboratory process into the real world with real world feedstocks. And I think a number of the producers are considering taking higher purity natural gas than what you're describing here in terms of a standard Middle Eastern or oil field production. And so that is an issue. I would say if you have a lot of H2S and such, you may want to consider doing the not doing the methane pyrolysis, but doing the reforming of natural gas and then combining it with a multi-purpose capture system, such as Shell has a CANSOLV process, which can capture sulfur dioxide and CO2 in an integrated fashion and do much of the gas cleanup that you're describing. And so the methane pyrolysis itself may be more relevant to those higher purity natural gas type feedstocks, but certainly the impact of those trace impurities is something that needs to be taken directly into account. And I guess similarly, the answer to your second question. So in terms of the criteria, pollutants and et cetera that come in the processing of the blue hydrogen. So again, if you're using a multi-purpose scrubber, much of that is removed in addition to the CO2 itself. Another thing that's being looked at is the electrification of the SMR. So you would use clean power generated electricity for the endothermic heating step in some of those processes. So that's also being looked at to be looking at firing a portion of that process. And of course, you can use the hydrogen itself as in portion to provide a fraction of the process heat in a more clean manner. That's being talked about for the methane pyrolysis. So so those are good points, and you know, it's important to provide the clean energy on the process side, in addition to the utility side, and to avoid some of those criteria pollutants that you're describing.
Thank you, Joe. Do we have other questions? Maybe before that, let me read a question from the online audience. I guess this is for Jorge. Relevant. So, how do you see the cogeneration of green and blue ammonia in the same plant to reduce the cost, since the green ammonia technology is still relatively immature?
So I think that we need to look at all those solutions. You can also think that you are integrating blue into the green plant. I mean, but at the end of the day, it's about making the best use we can with the renewable energy that we have.
So the question is that, do you see the potential for them to be co-produced in the same site, at the same site?
Absolutely. Absolutely. You could generate more heat by using more air, so that at the end you will combust a little bit more of natural gas, but you will replace that with green hydrogen. Yes.
And there's also talk of using the oxygen from the electrolysis and the partial oxidation for the methane reforming. That's a lot of capital intensity.
That's a good point. That's a very good point.
My question is to Pavel. What do you think about the in-situ combustion? Is it picking up after this hydrogen revolution? What is the cost and then the feasibility of this system? Like the in-situ combustion, let's say you do it and you spend a lot of money, and then how much hydrogen you're going to generate, and is it going to be feasible?
You mean swapping hydrogen for diesel and natural gas in the overall economy? Is that what you're referring to?
In the subsurface.
I see. Yeah. So yeah, there's certainly some articles out there that have very, very low costs, and so it's very intriguing. I did EOR early in my career, and it's quite difficult to control things in the subsurface. And so there are different approaches to that. Some are more controlled, you know, inside a wellhead versus others. And so I would say the controlled approach is certainly interesting. And the so-called fire flooding is going to be very difficult to control if you're doing it in the reservoir itself. So I don't think that that's making a lot of the mainstream consideration, but you know, being an R&D person, you always look at how you can bring something like that into the mainstream, and what would it take to be able to do it controllably and safely.
Thank you all for a very interesting presentation. This question is for to Christopher. There is a talk about critical metals and supply chain problems when it comes to rare metals in particular for electrolyzers. Do you see this a major issue for PEM in particular, and what solutions do you think envisage in the near future?
So it's definitely an issue, and while it's not a problem right now in the moment, it will be, and so that will affect our ability to really deploy this technology at large scale in the future. And so there are active programs and projects right now by our federal government and other funding agencies to look at this in maybe two ways. How do we get better utilization of the materials that we have available to us today, and that means with this limited amount of iridium or platinum, how can we use that more and stretch it by essentially coming up with methodologies that use less in each of our devices? But that only bridges us for a while. And then on the other end, there are active projects right now that are looking to remove iridium and platinum and look at other materials of construction, catalysts, and others that can provide the same activity and the same efficiency. But those are several years out. They're very immature, but it has been acknowledged as an issue to the large deployment of this technology. And hopefully some of our smart researchers at universities around the world and national labs are going to help to resolve that. But it will become an issue in large scale deployment for sure.
Thank you, Chris. So let me ask a quick question to Joe. You mentioned hydrogen has the indirect global warming potential. How do you see this playing a factor in the future consideration of hydrogen economy?
Yeah, it's in our report on infrastructure that we're doing right now for the National Academy, and it can impact your decision on how far you want to be transporting hydrogen to site of deployment, and then what are your assurances for that? And so siting and distance of transport, centralized versus distributed, it's going to push the technology development in terms of the pipeline or the liquid hydrogen distribution systems to assure that those leakages are minimized. Again, you can't afford to leak a lot of hydrogen because of the cost alone, but and it may push some of the considerations towards more distributed production that would favor perhaps electrolyzers for some the remote applications. And the issue is it's becoming part of the public discourse and news. And so, it becomes an issue that you have to address with stakeholders in your project planning. I think it's manageable for blue hydrogen, but you will have to address that with your stakeholder group and provide those estimates of what those controls will be.
Okay, thank you. We have the next question.
I have a question to you, Jorge. So we talk about the possible leaks of the hydrogen. And my question that ammonia can be considered as a good carrier of the hydrogen for the remote applications and for the beacons and also small scale generation of the hydrogen. But my question that since we cannot achieve 100% of the conversion, so that means that we might have still hydrogen and also ammonia in a nitrogen stream that goes out of the reactor. Have you considered how can we still utilize or to treat that nitrogen enriched stream in order to achieve a safe operation? And have you considered different applications of that stream, like for making fertilizers, just to find a good balance between the enough good conversion of ammonia to hydrogen and still a certain benefits for the treating of that nitrogen stream into the new products?
So first, the part on emitting ammonia. We have analyzed thoroughly the exit stream, the retentate side of our reactor, and also the permeate. When you operate a reactor properly, we do not even analyze ppms of ammonia. Did I switch it off? Yeah. Okay. So we have gone through the point of actually trying to scrap any ammonia on sulfuric acid and then do analysis of nitrates in that sulfuric acid. We haven't seen any. So a huge advantage of membrane reactors is that you can push the reaction over to the 100% conversion, because you can cheat thermodynamics in that sense, right? So that is absolutely not a problem. The second thing is, how do you want to have your hydrogen? That reaction has a huge energy need in terms of heat, is relatively highly endothermic. So worst case scenario, whatever the hydrogen that is in your retentate, You just burn it and generate heat to run the reaction. Best case scenario, you use a fuel cell and produce electricity. But that is, I don't see that as a problem. Then if you want to recover more hydrogen and you are interested in hydrogen at 1 bar of pressure, then run the permeate at 1 bar and 95% to 98% of your hydrogen, depending on the pressure that you have in the retentate, is going to permeate through the other side. So there's a lot of games that you can play.
Let's come back to the my second part. So you mentioned that ammonia also used as a fertilizer. The thing that it might be a same carrier to make hydrogen and also a fertilizers afterwards. Have you considered the balance when we can convert only part of the ammonia for the hydrogen, and remaining ammonia might be still be in the nitrogen stream in order to make a fertilizer? So because 100% of the conversion might be also quite tricky with the size of the membranes and also energy.
So about all this, only, so you are talking about fertilizers versus hydrogen transport. Yeah, I mean, all this makes only sense if we build 1,000 more ammonia producing plants, right? If not, it doesn't make any sense. We are going to continue needing fertilizers. So obviously that's for new, as you start producing more hydrogen and as you start needing more hydrogen for other applications, then what we are proposing is that new ammonia plants obviously will need to be built.
Yeah, this can be an ongoing discussion.
The scales are completely different, right? So ammonia for fertilizers, you are talking about 150 million tons per year. If we will go full scale with hydrogen, you could be 2 orders of magnitude over that.
Okay, thank you. So the next question is for Chris. Chris, how do you see do you see the target cost of $1.5 per kg of hydrogen realistic? And then how would you comment on the challenges faced by the seawater electrolysis?
So as far as the cost targets go, I touched upon this very lightly in the presentation that I gave, but we have an internal goal to reach that by 2025, and we're ahead of plan right now. So we expect to be able to reach that based on the reduction in electricity costs that we're seeing, as well as some of the reduction in the actual expense of the equipment that we're seeing. So the $1.5 per kilogram is very achievable, and we expect to be there in about 2 years. There is a longer term goal in the United States to reach $1 a kilogram by about 2030, and we believe on the PEM side that we're on track to meet that as well within that time frame. So and that most of that is being done through technical development and scale and automation to reduce the cost. The on the saltwater electrolysis side, so this is an area that I don't have a lot of experience with, and I know it just gets discussed routinely, but salt water cannot be fed into an electrolyzer. So it's really a technology on the front end that can do the desalination of the water through existing RO processes or some electrolytic process, but you can't feed seawater directly into an electrolysis device, else it'll destroy the membrane. So there has to be a technology on the front end that can take seawater and process that for use in our electrolyzers. And so we have one project, it's not installed yet, but it's on a oil rig in the middle of the ocean. And that'll be the first demonstration of that type of technology where we're taking seawater directly, purifying it, and then providing it directly to an electrolyzer in a one package solution.
Thank you. We will take one final question.
Can I ask a question here?
Jeremy.
Hi, my name is Jeremy. I'm a research scientist in the Catalysis Center. This question is for Chris. Recently, in the last couple of years, we've seen this booming of the emergence of some anion exchange membrane technology. What are your and your industry's views on its commercialization?
Yeah.
Thanks.
Yeah, so thank you for the question. I didn't include this in the presentation because it's fairly immature, but it is an area of research that we are actively evaluating. I have 3 active programs right now with the Department of Energy to research alkaline exchange membrane technology. It's obviously very intriguing, right? Because it allows you to move away from the rare earth metal catalyst and to cheaper materials construction. But the technology is very, very early stage. We see it as a potential disruptor to PEM technology, and that's why we want to pursue it. So we have several projects right now evaluating the technology, but our roadmap certainly shows that as being implemented in a manufacturing capacity for commercial systems, probably in the 5 to 10 year time frame, I think. So it's still that far away, but there is a lot of research that we do, and there's a lot of research being done in the community right now to advance that.
Thanks.
I hope that helps.
Really, the last one. Yeah.
Yeah, thanks for the presenter for the informative presentation. This is Ibrahim, chemical engineering master student. My question goes to Chris. At a large scale electrolyzer, what would you do with the oxygen produced? Thank you.
Sure. So it's interesting. When we used to make our smaller systems, nobody really wanted the oxygen because there's much cheaper ways to make it. But as the systems have grown in scale, there's been much more interest in trying to use that high volume of oxygen that's being generated. And so that installation in Spain is one of the first units that we've deployed, not only at that scale, but the customer requested that they have the oxygen available so they can use it in a nitric acid process at the same facility. And so at a certain scale, the generation of oxygen starts to become an interesting opportunity for our customers and the markets out there. So we see the oxygen as a byproduct of the hydrogen generation, providing value to other processes that are at some of these large plants.
Okay, with this last question, I would like to conclude today's seminar series. And please join me thanking all 3 speakers for wonderful presentations today. And then we will see you in the next seminar series in 2 weeks. Thank you very much.